there's no secret about this. Finding theorems is hard. People devote their lives to it. Finding proofs of theorems is hard. People devote their lives to it. Writing up the proof of a theorem is hard, and I don't know that anyone devotes their life to it, but it is something that demands some practice and proficiency. And in many ways, you can make this routine, and so you can focus on the honest hard stuff. Some of it's almost algorithmic, and so let's look at some problems. So you've been looking at some problems from section 3.7 of our textbook, and all three are induction problems. And although one, there's another way that we could do, but we already did it by induction. And so let's look at them. And the proofs in this case are as straightforward as these kinds of things can be to find. It's not like you have to search around and read a 1,000-page book on something before you can figure out what the proof is. The proofs are one or two lines, but it's very easy when you're explaining what you've done in a proof to write nonsense. You have to be extremely precise about the way you express the thoughts that you've had. It's almost like you have to talk to a compiler who's going to tell you that there's a syntax error, only we're not such great compilers. And so with practice, you can recognize a syntax error or a spelling error or something like that, or a grammar error or a logic error. And that's a lot of errors, isn't it? Anyway, with practice, you can do better. So one of the things that you can do that can't be said too much is never write out a proof of a theorem without saying what it is that you're trying to prove. Otherwise, there's no context to it, and you won't be able to read it, and no one else will be able to understand it. One thing that you can do that will make that work out nicely is, as you're looking at the theorem that you're trying to prove, have a very clear idea. This isn't always easy, but this is what you need to aim at. A very clear idea of what you've been given, what facts you know, and a very clear idea of what you're trying to prove, where you're trying to get to, and you need to state those quite explicitly, even in your own notes. Home Alone, windows drawn, shades drawn. Put them in your own notes. This is what I need. This is what I am given. And that really can be very, very helpful. And then you need to pay attention. There's no symbol on this page that isn't there for a meaning or for a reason that has a meaning. And so if you skip over a symbol, now you're doing something else. So the level of language precision that you're being called on to exercise is much greater than it is in normal life. Okay, so let's look at these. We've got these problems from section 3.7. And the first one, and I'm going to follow my own rule because it's a really good rule. It's not my rule. It's a rule of common sense. Is you're given for n greater than or equal to 1 that you need to prove that the following sum, I'm going to use j equals 1 to n, and the terms of the sum are j times j factorial. You probably need to be careful with the parentheses here. Anyway, this sum has a nice, by the way, if n is large at all, these numbers are impossibly huge. So you're not going to be able to do any examples to help you understand what's going on with this sum. And anyway, this has a nice closed form expression, and the closed form expression is n plus 1 factorial minus 1. 1 less than n plus 1 factorial. So there's the sum, there's the closed form, and there really is no other way to do this, to understand that this is true. Now, I'm not sure where this came from, and so I won't even speculate about it. So when you have the situation where you have a for all n greater than or equal to 1, there's an implicit for all there, but nobody writes that. So you need to get used to saying, oh yeah, that means for all n. For all natural numbers, something's true. Induction. If you don't like that, you should try induction. And the alternative method is induction. That's it. Nothing else works. And so that's our situation. So we have to prove, so what I've written here, I'm going to specify as being a logical statement, not a formula. It's a logical statement, P of n. So for any n, this is true or false. You're trying to prove it's always true, but it's a statement that depends on n. Okay. So we need to prove two things. This is typical for induction. This always happens with induction. In this case, we need to prove P of 1, and then we need to prove that P of n implies P of n plus 1. So those are the two steps to induction. This is like a little for loop with an increment, only it goes on forever. So those are the two steps. We need to prove that this is true when n is 1. And we need to prove that if this is true for a certain n, then it is true for the next n. So let's keep working with that. And so for P of 1 is pretty straightforward. I'm just going to check. That's often the case with the base cases. You just check it. P of 1 is the claim that, well, let's see, it's going to be the sum from j equals 1 to 1. So that just means 1 times 1 factorial is equal to 2 factorial minus 1. Now, I've done something very important here that your life will be a lot easier in working with these things if you do this. It's not about pleasing me. This is about making sure that you are doing the proper things in terms of reasoning. I wrote claim. That's the claim. I'm not saying that it's true yet. If you just write it, you're saying that it's true, and that's wrong. It is a claim. So say claim. And then we'll just check it. And well, that's obviously true because just doing a little arithmetic, 1 times 1 equals 2 minus 1. So not much to write there, but there it is. So I'm claiming that it's true, and then I checked that it's true. Okay. The other part is that P of n implies P of n plus 1. So you're going to assume that this is true for a certain n and prove that it's true for the next n. And so let me be clear in the way you need to be clear about what's going on here, is to say what you're given, and I'm going to write it out in symbols, as a symbol. You're given that the sum j equals 1 to n of j times j factorial is equal to this funny thing, n plus 1 factorial, gigantic number, minus 1. And so I have said that this has been given. I am supposed to use this. If I get through the proof and I haven't used this, then I'm probably wrong. Not always, because sometimes people include hypotheses that aren't necessary, but probably wrong if you haven't used this. Okay, so what I need to do is, and I'm just going to be writing this because it's a one-step proof. What I need to do is to look at, this is the thing I'm curious about, the sum j equals 1 to n plus 1 j times j factorial. Now this is a distinction that is in the smallest font we commonly use. And so I've tried to highlight it by color. So we're given something where the sum goes up to n, but we need something where the sum goes up to n plus 1. Well, that means there's one more term. And so when I look at that, excuse me, there's a spider on my page. It's gone now, in a humane way. Anyway, when I look at that, I'm just going to write out, this is a common thing that you do with sums. I'm going to write out what it is that I'm interested in. So I'm interested in 1 times 1 factorial plus 2 times 2 factorial. And then this is kind of a standard trick, so I'm going to do it. I know about what happens out to n, and I'm interested in what happens at n plus 1. So I split this part off, and we can do that pretty simply. The notation for this last one is kind of wickety-whack. So this is where j is n plus 1, so I'm supposed to take j and then j factorial. Well, j factorial, you definitely need parentheses about that because you're trying to, what do you do first? Well, first you're going to take n plus 1, and then you're going to do that factorial, and then you're going to multiply that by n plus 1 again. So this is actually a double parentheses situation. So I'm going to take n plus 1, then I'm going to take its factorial, and then I'm going to multiply that by this other n plus 1. And so that's the situation. So this is the arithmetic expression that we're interested in. And we can pretty much jump straight ahead. We can say that this is equal to, and the first few terms here are something that we can handle because we've been told how to handle them. So we've been given, there it is, what happens when you go up to n, and here we're going up to n. So we're just going to substitute what we've been told is the closed form for that expression. So the closed form is n plus 1 factorial minus 1. And then there's still another term here, so I'm going to write that as n plus 1 times, double parenthesis, n plus 1 factorial. So I have used the induction hypothesis right here. I've taken these first n terms and replaced them with the closed form that I was told to assume is true. So now, if that's not true, then your reasoning is still correct, but the conclusion may not be correct. But in fact, it is. So this is the induction step right here. That's it. I've been told what to do when there are n terms, so I do it. And now comes a little bit of tricky algebra. It's actually very simple algebra, but it's really tricky to write it down. And so what I'm going to notice here is I've got 3 terms. 2 of them have factors of n plus 1 factorial. So the middle term does not. So here's an n plus 1 factorial. Here is a term that has nothing to do with 1 over n plus 1 with n over n plus 1 factorial. And here is another term that has an n plus 1 factorial factor. So I can factor n plus 1 factorial out of these two using the distributive law. And what we get here is, well, we're going to have n plus 1 factorial, and then some other stuff minus 1. So this is my philosophy of doing the parentheses first. So I'm going to pull out the n plus 1 factorial from these two terms. With the distributive law here, what we have, the first time n plus 1 factorial appears there, it's got a 1. It's 1 times n plus 1 factorial. And the second time, it has n plus 1. So this is 1 times n plus 1 factorial. This is n plus 1 times 1 plus 1 factorial. And so that's what I've reflected here inside the brackets. Okay, well now we're off to the races because 1 plus n plus 1 is n plus 1 plus 1. Everyone wants to say n plus 2, but that's actually incorrect. It's n plus 1 plus 1. The statement, when I write it down again, you'll see that that's actually what it should be. So this is n plus 1 factorial minus 1 as desired. There are other ways of saying this, but there it is. This has kind of become a run-on sentence, but there's the deal. So I need to know about what happens when we have n plus 1 terms. So I write out n plus 1 terms, and I do a little bit of logic in the form of using the induction hypothesis, and then a little bit of algebra. and come up with n plus 1 factorial. And I'm going to insist on writing it this way, and I'll show you why. And the reason is that I'm going to write out what this p of n plus 1, what happens when you have n plus 1 terms. So p of n plus 1 is the assertion that the sum, j equals 1 to n plus 1, of j times j factorial, so that's the left side, is equal to, and the right side is, you got to kind of take off your computing gloves and say, the assertion here is that I'm going to take the factorial of 1 more than the upper limit of the sum. So if the upper limit of the sum is n plus 1, 1 more than that is n plus 1 factorial minus 1. And we have established that this is true by induction. So, well, I'm going to scan this so you can read it at your leisure. Let me, this is getting to be a little long. I'm going to skip number 4 for now. And number 4 has a very similar logical structure. And so you pull off what you're given, you do the induction hypothesis to that, and then you do the algebra to see what happens with what's left over. But let me make sure that we get the correct statement for problem number 6. A lot of people didn't understand the statement of the problem, and so they did stuff that might have been interesting, but it wasn't addressing the problem at hand. So what we have is, it's if n is greater than or equal to 2, the negation of a bunch of propositions anded together, anded, not nanded, that's something different, is equivalent to the negation of the first one, it's or the negation of the second one, or ... or the negation of the last one. So this is what you're trying to prove. And so this is an induction proof. It says so right here, because you're looking for all n greater than or equal to 2. The proposition doesn't make sense if n is 1, so that's why we started with n is greater than or equal to 2. So you have a base case, p of 2, and that's De Morgan's law. You don't have to prove that. You can say, oh, p of 2 is De Morgan's law. You're done. A lot of people proved De Morgan's law, but that's not what it was asking you to do. De Morgan's law applies to the and of 2 propositions, and now we have more than 2 propositions, and we're going to say that this works for any number of propositions. So we also need, and I'm going to write need, that p of n implies p of n plus 1. So that's induction. So a lot of people got hung up on this, which all you had to do was say De Morgan's law. And a lot of people didn't ever get to this step. And so that's the structure of this going on. This is a induction. You start with a known base case, and then you induct your way up so that this works for any number of propositions. And so there's a, let me see if I can get this done lickety-split. I don't like to make these videos too long, but here's the deal. So I'm given p of 1. So I'm given that the negation of this conjunction of n things is equivalent to the negation of the first, or the negation of the last. So I'm given that. That's the induction hypothesis. The induction hypothesis says that p of n implies p of n plus 1. So you're given that p of n is true, and now you need to establish p of n plus 1 is true. And there's a little eyeball trick. So it's like a trick of refocusing. So we're going to start by looking at the negation of, we're going to have n plus 1 propositions, and we've been through this enough so we know we do the first n and then one more. So this is going to be this is what we're asked about, and what we're going to do is split that up, and we're going to split that up in a colorful way, and this is this, I'm saying this is equivalent. This is something that almost requires no proof. And so here's the deal. Here's the colorful way. I'm doing the parentheses first. I'm going to split this up into an and involving two factors. Factors, terms, propositions, snowballs, I don't know. Anyway, and one of them is I'm sorry, we're negating that whole thing. The negation of P1 through Pn, and the last thing is P sub n plus 1. So it's a little bit small to read here. So I've got n plus 1 of them, so I split off the first n. That's what you almost always do in some kind of induction. And that's the last one. It's there, hanging out there by itself, saying, hey, don't forget about me. So now, and I'm negating that. Now, this is, as the parentheses say, this is just a refocus. Oh, I'm going to apply De Morgan's law to this thing in the green parentheses, and that has two factors. It's got the one in parentheses and the lonely one, and so we can apply De Morgan's law right here, and so what we get is that we're going to get the negation of P1 or the negation of P sub n, or the negation of P sub n plus 1. So that might be a little hard to read. So I applied De Morgan's law here to these two things. So I have the negation of the thing in parentheses. Well, that's this by the induction hypothesis, and then there's the rest of the De Morgan's law. So that should get you started thinking about this in the right way. And of course, I'll scan this so that you can study it more leisurely. But you gotta be aware of what's going on with induction. It tells you you're going to do induction. It says you're going to do induction. It doesn't say, oh, you're going to do induction. It says for every natural number, or for every n greater than or equal to 2, something like that. That's telling you you're going to do induction. And then once you recognize that, you split off the base case and the induction case, and be very, very clear both to yourself and to whoever is reading your work what it is that you're given and what it is that you're trying to prove.